So we've seen that the optimization problem that we are solving now is this. W star equals to the W that minimizes the logistic loss I equals to 1 to n log of 1 plus exp of minus yi w transpose xi, right? So let me call this term as zi just for simplicity, just for brevity, basically to write it much more elegantly, plus lambda times the L2 norm square of W, right? So just to explain you the notation, this is your loss function, right? This part is your, it's also called as logistic loss. Okay, I'll explain you why it is called loss when we look at the loss minimization interpretation of logistic regression, right? This is called the logistic loss. This is called the L2 regularizer. Why is it called L2 regularizer? Because we are using the L2 norm of W to regularize, right? So just to quickly recap what we learned in the previous video, this is to ensure that Zi's don't tend to plus infinity. Or in other words, this is nothing but Wi's don't tend to plus infinity or Wi's don't tend to minus infinity. We don't want them to happen, and we don't want overfitting to happen to our training data, and hence we are introducing the regularization. Now the immediate question is, why use only L2 regularizer, right? Are there other alternatives? Are there other viable alternatives to L2 regularization? There is a very popular alternative. There is a very popular alternative called as L1 regularization. I'll explain you what is L1 regularization and why it is popular in a little while, right? So in L1 regularization, what we get is this. What we do here is, instead of using W2 square norm for regularization, instead of this, we use W1 norm, the one norm for regularization. And to quickly recap, what is one norm of a vector? We saw this when we learned about Minkowski distance, right? A one norm of a vector is nothing but summation over I equals to 1 to d. Because W has d, W is a d-dimensional vector, the absolute value of Wi, right? In this case, what happens? Your optimization problem becomes argmin of W, your logistic loss across your training data, your logistic loss for training data, right? Which is the first term, right? This is your logistic loss for the training data, right? Plus lambda times L1 norm of W, right? So this is now called as L1 regularizer, and the logistic loss function stays the same. You don't fiddle around much with the loss function. You're only changing the L1, the regularization part. Here again, your lambda is your hyperparameter. This is a very popular regularization alternative to L2 regularization. So you'll notice that since you have absolute value function here, whether Wi is tending to plus infinity or Wi is tending to minus infinity, right? The absolute value will always become plus infinity. And since we have it as a regularizer, this even L1 regularizer will avoid your Wi to go to plus infinity or to minus infinity. It will avoid both of them, right? Just it serves the same purpose as your L2 regularizer, right? It serves the same purpose as L2 regularizer, but it has one very major advantage. That's called sparsity. That advantage is called sparsity. Let me explain you what is sparsity mean first. Then I'll explain you that L1 regularizer creates sparsity. The proof of it, we'll see it little later. What does sparsity mean? Imagine you have a vector W, the final vector, the optimal vector W, which is a d-dimensional vector WD. A solution to logistic regression, I'll just call it LR for now, is said to be sparse if many Wi's are 0, right? This is nothing but the sparsity of the vector W. A solution to logistic regression is nothing but what? Is nothing but your optimal W, right? A solution to logistic regression is nothing but finding your W star or the optimal W. And the optimal W is said to be sparse if many of the Wi's or W star i's, okay, are zero. So if your W vector is sparse, then the solution to logistic regression is said to be sparse. Okay, that's what I mean by sparsity in logistic regression, right? Number one. Number two is through a lot of experiments. Again, we can prove this. What happens is this: if we use L1 regularization in logistic regression, all the unimportant features, all the unimportant or the less important features, all the unimportant or less important features, all the less important features, all the less important features become zero. Their values become, what I mean by less important features, WIs. Suppose, imagine if I have a WI, imagine if I have features F1, F2, so on, so forth, FD. Corresponding to each of these dimensions or each of these features, I have a component to my weight vector, right? I have a component to my weight vector. Suppose let's assume feature I correspondingly my weight vector Wi. Imagine if feature I is less important. Imagine if this is less important, right? Then immediately Wi will become equal to 0 if L1 regularization is used. If L1 regularization is used. If L2 is used, if L2 regularization is used, right? Wi becomes a small value. Wi becomes a small value, but not necessarily 0. But not necessarily 0. So L1 regularization is often used in logistic regression when we want a sparsity. If we want all the unimportant features weights, if we want the weights of all the unimportant features to become 0, we tend to employ L1 regularization instead of L2 regularization. Now you might ask, why does that happen? So the question here is, why does L1 regularization create sparsity in W as compared to L2 regularization, right? You said you made the statement, but you never proved it. What we will do here is we'll prove this statement. We'll prove this statement logically or algebraically when we learn optimization. So we learn optimization in the next chapter. When we learn optimization, I will prove this statement intuitively, not like rigorous mathematically, but I'll prove this statement intuitively that L1 creates sparsity in your weight vector as compared to L2 regularization. Till then, you'll have to wait. But you'll see a lot of times that people use L1 regularized, people often use L1 regularized logistic regression instead of L2 regularization. There is another alternative called as elastic net. This is not a neural network. It's called an elastic net. What people do is sometimes they say, why should I choose either L1 or L2? What if I have both in my optimization problem, right? The way it works is they take W star equals to argmin, right? Summation I equals to 1 to n, my logistic loss function, log of 1 plus exp of minus zi, right? Plus lambda 1 times L1 norm plus lambda 2 times L2 norm square. So they try to solve this problem wherein they have both L1 norm and L2 norm. So this is your L1 norm, this is your L2 norm. They tend to have both of them sometimes. Now when they do this, you have two hyperparameters. When you have this, you have two hyperparameters. You no more have one hyperparameter. You have two hyperparameters, lambda 1 and lambda 2. that you need to do, that you need to find the optimal lambdas now, using again cross validation and things like that, right? So it's no more trivial again now. So you have two hyperparameters here, one hyperparameter corresponding to L1 norm, other hyperparameter corresponding to L2 norm. But this is solvable. Let me tell you that it is possible to find lambda 1 and lambda 2. It's possible. So such a system where you have both L1 norm and L2 norm in your optimization problem is called the elastic net formulation of logistic regression.